So if you remember, we split the dividend cash flow stream into two parts. We've already calculated the present value for dividends from time 2 to time 12. Now we need to deal with the dividends after the split. In other words, the dividends from time 13 onwards. And remember that these dividends continue in perpetuity. So we follow the exact same recipe. I'm going to denote the present value of this dividend stream as P2. And I'm going to discount all of these cash flows 2 times 0. Now the first cash flow is D times 1.06 to the power 10 multiplied by 1.03 because the growth rate has changed. Now this cash flow happens at time 13, so I need to discount for 13 years. The second payment is the initial dividend times 1.06 to the power 10, so adding 10 years of growth, and then we have 2 years of growth at 3%. We need to discount this value from time 14 to time 0, so that is discounting for 14 years at an annual rate of 7%. These terms will just continue, and I'm sure by now you can see the pattern. Remember that these cash flows continue in perpetuity, which means they never end. So we assume that this company never goes bankrupt and just continues to pay dividends. Once again, we are going to solve for this equation, the summation, by using compound increasing annuity theory. But we know that we need the exponent of the discount factor and the growth factor to be the same. The first thing we need to do is to notice this common term in each of these factors, which is the initial dividend of D times 1.06 to the power 10, so in other words, with 10 years worth of growth. And each of the terms has this factor. So that means we can take out D times 1.06 to the power 10 as a common factor, and we are left with 1.03 multiplied by V to the power 13 plus 1.03 to the power 2 or squared multiplied by V at 7% to the power 14, and so on and so on. The reason this is important is because a compound annuity can only cater for two items: one discount factor and one growth factor. And we know that for the compound increasing annuity formula to apply, the two exponents need to be equal. Now, because there's a 6% and a 3% involved when writing down this equation, we have to take one of these, we have to eliminate one of these to work with a compound annuity formula. But you can see that the 1.06 to the power 10 is actually a constant. It is not in the following form because the exponent of 1.06 remains equal to 10. It's a flat number. So that's why we include that in a constant that is outside of the brackets. Then we are left with the pattern, a discount rate to some power multiplied by 1 plus a growth rate to some other power. For this first term, that would just be 1. Again, we are using the same trick to get these two exponents to be the same. So let's tackle term 1 of this equation inside of the brackets. So that is 1.03 multiplied by V at 7% to the power 13. That is just this number. Now my preference is to reduce the exponent of the discount factor. So we need the exponent of the discount factor to be 1 in this case. So we can split V to the power 13 into two values. V to the power 12 multiplied by V to the power 1. And then we're still left with 1.03. Now we have the form that we require for the compound annuity. which is discount factor times 1 plus growth factor, and both of them are raised to the power 1. Let's see if we do the same for term 2, if this works out. Term 2 is equal to 1.03 to the power 2 multiplied by v at 7% to the power 14. So I'm using this term. If we follow the same logic, we can extract v to the power 12. We can multiply that by v to the power 2 at 7%. And because the laws of exponents says that you simply add the two exponents, when you multiply, we get back v to the power 14. So in other words, this factor is exactly the same as the factor above, except that we still need the 1.03 to the power 2. Now you can see that we have a term where both of the exponents are the same. So taking out v to the power 12 as a common denominator from the formula above will yield the desired form that we need for the compound increasing annuity. So let's rework this equation above. Simply d times 1.06 to the power 10. So that is our base starting value for each of these factors. Then we said we will take out v to the power 12 as a common factor from each of these terms. So what remains is we've already seen this 1.03 times v to the power 1 plus, and the second term becomes 1.03 times v squared at 7%. And remember, this is a perpetuity which continues indefinitely. So remember, the theory behind compound increasing annuities is fairly simple. We take 1.03 times v at 7% and we set that equal to a new discount factor which has a new interest rate associated with it. It will not be J, it will be some other interest rate. J was based on 1.06 multiplied by V at 7%, if you remember. So this term will simply become W, this term will become W squared, and so on and so forth. Now there are two important things that we need to determine. Is this an annuity in advance or is this an annuity in arrears? So in other words, are payments made at the start of each year or at the end of each year? Now it's very clear that the first payment is discounted for 1 year because we have W to the power 1. So that means we are dealing with an annuity in arrears. The second question that we need to answer is we need to figure out what the term of the annuity is. Now, in the previous formula, we had a finite number of cash flows. For the values that follow the yellow bar, we have an infinite number of dividend payments that are being added. So the term is an infinite annuity, also called a perpetuity. So the annuity type that we need in this case is not an annuity in advance. So in other words, no dots above the A, but an annuity in arrears, and the term is infinite. The formula for this annuity is fairly simple, 1 over I. And once we know this, it's fairly easy to condense the summation in the square brackets to this simple formula. Let me show you what I mean. So remember, in our case, the interest rate is actually K and not I. This may seem like semantics, but it's very important that you realize that this is a new interest rate which is dependent on the discount factor W. So calculating for K will be very similar to what we did previously. We know that 1 plus K to the power minus 1, which is our new discount factor, and this will equal 1.03 multiplied by 1.07, which is our interest rate, to the power minus 1. If you simplify this, K is equal to 1.07 over 1.03 minus 1, and that is 0.03 8, 8, etc. So now it's just a matter of simply plugging in the numbers. We remember that the initial dividend is 20 US cents times 1.06 to the power 10. Importantly, the discount factor that we took out as a common factor needs to use the original rate of return provided by the problem, which is 7%. Then we've just figured out that all of this inside of the brackets can be substituted by an annuity, actually a perpetuity, working off an interest rate of K. And we also know that this is just 1 divided by K. And we already know what the value of K is. If you work this out on your calculator, you obtain a value of 4.095 with some decimals. Now the price of the share is simply equal to the present value that we calculated for the first annuity stream plus the present value that we calculated for the second annuity stream. If you can't quite remember what that was, let me just go back. So your first annuity stream is all of the dividend payments up until the yellow bar, so up until time 12. And your second annuity stream is all the dividend payments that follow the yellow bar. We had to do this because the growth rate changes after the first 10 years or following that yellow bar. Provided that you haven't made any rounding errors, you should get an answer of 5.92. Now, importantly, the question asks us to calculate the price of the share to the nearest US cent, so rounded to 2 decimal values. Many students lost marks by not doing this final step. So if we do round this to 2 decimal places, we obtain a value 5.93. So that's it for this masterclass. I hope you found this video useful. I would love to hear from you, so please leave me comments and suggestions on what you'd like to learn next. Good luck with your exam preparations and hope to see you soon.